So now this is the time to write a test bench for this module. So as usual, first I will create a new file. So click on this button. Now save this file as a VHDL file. So I will go to this UART project. And now we are writing a test bench. So I will choose this test bench folder. Now I will select the file type. So this is VHDL. So basic hardware description language I have to select. Now I will give it some name. So suppose this is the test bench for UART receiver. Okay. Now save. Now I will copy this library declaration and entity declaration from here, from our UART underscore receiver module, and I will paste it here. And I will update the entity name to TB. Now I will copy this. I will use it here. And sorry, it is not pasted, I think. Okay, this is not copied. So this is our AND entity, and this is our architecture body. So let's complete it first. So begin and add architecture. So this is and behave. Okay, so that's good. Now we need to define this entity as a component here in this architecture section. So I will copy this and I will replace this entity with component and this entity name with component. So this is a component here, and I do not need any generic and port here in this entity for this test bench. Okay. Now I will declare all the signals used in this UART receiver module. So these are the signals here. So let's declare them first. So these all are signals. Signal. This is again signal, and the out is also our signal. Because these are signals, so we do not need to write any direction here because these will give the syntax error. So let's remove everything related to direction, and we will also instantiate this clock, or I will give some initial value to this clock because I want to generate a clock signal of 50 megahertz. So what I will write that this clock is actually not a clock after 10 nanoseconds. So that will generate a 50 megahertz of clock signal for us, right? And next, first we will instantiate the component for this test bench. So I will copy this part and let's instantiate it. So this will be our UUT, unit under test. Now remove this is keyword. Now generate map. So this will be very straightforward. Our data width. So our data width will be 8 for this module, for this receiver module. Our system clock frequency will be 50 megahertz, and our baud rate will be 115200. Okay, so remove this semicolon from here. Now port map. This is very straightforward. Clock is connected to clock. Reset is connected to reset, comma. DIN is connected to DIN. RX IRQ clear will be connected to the same signal. RX IRQ will be connected to the RX IRQ, and DOut will be connected to DOut, right? And we do not need this last statement, so let's remove this. Okay, so that's good. We have instantiated our unit under test. And now we will drive our input signals, right? So for this, I will use a process block. So first I will write the structure for this process. So give it some name. So this is our test process, and this is the process. And now I'm not writing any port or any signal in the sensitivity list because I'm going to use the wait statement here in this process block. Okay. So process now begin. In the last, we will have this wait statement, and in the last and process. Okay, so that's good. So first I will trigger the reset condition first for the 100 nanosecond. Then I will release the reset condition for another 100 nanosecond. And then we will start receiving the data on the day inputs. Okay, so first the reset condition. So our reset will be high. Also, I want our din to be in ideal state. So din is high. And let's say this Rx IRQ clear, that is also 0 here. Now I want to wait for 100 nanosecond. And after this 100 nanosecond, this reset condition will be removed. So reset is 0. And I will wait again for 100 nanosecond. Okay. Now, after this point of time, I will receive the start bit at the receiving point. So our din will be 0, and then I will wait for the 1 bit period. And the bit period is 8.7 microsecond for the baud rate of 115200. So I will wait for 8.7 microsecond. And now I have to transfer 8 bits one by one. And that will be our actual data that we are going to receive at this UART receiver module, right? So what I will do that I will create another signal, that is signal, and let's say this is our data which we are going to receive, and that is std logic vector. Now let's say this is 7 down to 0, and let's remove this 7 down to 0. Okay, this means we are about to receive 8-bit data, right? And let's say our data is, this data is 10101010. Okay, so this is AA in hex. Okay, so this is our data which we are going to receive at this UART receiver module. Okay, so what I will do, so one thing what you can do, that you can write that din will be our data index 0, and then wait for 8.7 microsecond. Then again you can copy this, paste this multiple times, and then you can update this one by one. So that's one thing you can do. Now we are sending this index 0 first because this is our LSB. So this is 7 and this is index 0. And RS-232 protocol sends the LSB first. So first this 0 will be received, then 1, then 0, and up to this MSB. Okay. So as I said, you can use multiple statement for this, or you can just use a for loop for this purpose. So what I will write that for I in 0 to 7 loop. Now I will use these two statements here, and finally and loop. And now I do not need all these statements copied 8 times, right? Now this din will be, okay, so that was our start bit. So let's leave it 0. I will use my for loop from here. So for I in 0 to 7 loop. Now these two statements and then and loop. So now you do not need to copy these two statements 8 times here. So what I will do, that this data 0 will be replaced by data I. Okay. And now once all the 8 bits are received, then we will have the stop bit, right? So din will be 1 for the stop bit or for the ideal state, and I will wait for another 8.7 microsecond, right? So now once we have received this start bit followed by the data lines and then stop bit, we will generate the interrupt request signal, right? So if you go to the UART receiver and if you look for the finite state machines here in the last, so you will see that when all the collection is done, then we will trigger this RX underscore IRQ, right? And this will be cleared when we insert this RX underscore IRQ underscore clear signal, right? So what I will do, that after this, I will clear this RX underscore IRQ underscore clear signal. So this will be 1. And now I wanted to give this clear pulse for 1 clock cycle. So what I will do, so I will wait until rising edge of clock. And once we have this rising edge of clock, then this RX clear will be 0. Okay. I also wanted to synchronize this RX IRQ clear signal with the rising edge of clock, because we do not know that when this 8.7 microseconds will be completed, if that comes at the rising edge of clock or not. And because everything is synchronized with the rising edge of clock here in the receiver module, so we have to wait for the rising edge of clock here before clearing this message or before clearing this signal. Okay, so I think everything is done. Let's save this file. Okay, we have the signal without the semicolon. Let's give a semicolon and then save it. Else everything looks good to me. Okay, let's save this and open this into the Model Sim Simulator. So again, right click on Add to Project and Existing File. Now click on Browse. Now go to this UART project. Now we have test bench to load this time. So I will click on this test bench folder and I will select this UART underscore receiver test bench. So let's rename this. I think what I have saved this. So UART receiver. Okay, so let's save this once again. Save as underscore test bench. Okay. Now we have the correct file. So let's save this, go to the model sim simulator, and we would be able to see this UART underscore RX underscore TV. Okay. Now open this file. Now click on OK. Okay. So we have this file listed here. Now right click, compile, compile selected. Okay. We come up with few errors. Okay. So it is complaining at line number 30 and 31. So let's go to 30 and 31. Oh, okay. So we have copied the signal declaration in between these two lines. So we have missing component section. So we need to add this component here and then we can declare the signals. Okay. Okay. So let's save this and close this. Once again, we will compile it. So compile, compile selected. Again, we have few more errors. Okay. Let's see what's the problem. Okay. Too many things. Control S, save. Now close this, recompile. Okay, so here you go. Our compilation of this UART underscore receiver test bench is successful now. Okay. So now this is the time to simulate our test bench in the forms of waveforms, and we will see that everything is working as per our expectation or not, right? So we will go to this library tab. We will look for the work library. So it is at the top. So we can see this UART underscore receiver underscore TB here. So I will right click here and then click on simulate. Okay, so we have this waveform window here. So I am really interested in this UUT, that is unit under test. And now I will select the important signal that are useful for our analysis. So I will select this clock, or let me select all the signals here. So we have this baud clock, and I will select this. Okay, and everything else. Okay, so these are the signals I'm interested. Let's drag them into the waveform. And let's simulate our program for 200 microsecond. I think that will be enough time for generating all the pulses and capturing all the input bits. So run for 200 microsecond. Let's see. Okay, so let's zoom out and let's see if we are getting pulses or not. Okay, so we can see that signals are changing. So we have enough data. So first what I will check that are we capturing the data in the middle of bit period or not, right? So for this, what I will use this baud clock, okay, and I will use this D in or this RX sync even. So this is I think better to take in. Now let's zoom out little. Okay, so let's see. Okay, so we have this baud clock as in first pulse here, and then we are generating multiple pulses. Okay, right? So what we have said that we are expecting to see this first pulse of this baud clock at half of the bit period and all the successive pulses at full bit period. Okay, so first let's quickly compare the time gap between the two pulses. So this is our first pulse. Okay, so now I will add a marker at the first pulse, and that should be around 4.3 microsecond something, because 8.7 microsecond is our 1 bit period. So the half bit period is around 4.35, right? Okay, so let's zoom a little more so that we can see a little better. Okay, so this is the triggering point, and this is our starting. Okay, so that is near about 4.35 or 4.36 microsecond. So that's good because I think we need to adjust it a little more, but I think this is 4.35. So that is under the acceptance variations. Okay, so that is fine. So we are getting the first pulse at near about half of the bit period. So that is 4.35 microsecond. So that's good. Next, we will look over the successive pulse. So let's move this here and let's move this marker here. So that should be near around 8.7 microsecond. Okay, so you can see that we are around 8.7 microsecond. So this is one complete bit period. Okay, and all the successive pulses looks to be at 8.7 microseconds, right? Okay, so these gaps, this gap are identical. So every gap is identical except this first one, because this first one is half of the bit period. Okay, so that's good. Now we will see if we are capturing the inputs at the middle of the baud clock or not. Okay, so if we look at this of this first pulse, so this is our baud clock and this is our input signal that we are going to capture. Okay, so this is 0 here, so that is good because that is our start bit. And next we are going to capture this. So this is 0 that we have captured here. So that is good again, because if you remember that the data we have at this test bench, that is 10101010. So the 0th index or the least significant bit is 0, right? So this, at this point we are getting the start bit and that is 0. And at this point we are getting the least significant bit and that is again 0. But when we are coming to the next pulse, so that is next pulse, and here we are receiving 1. So that is correct because the first index of this data is 1. Okay, so that one is received here. Okay, and if you see that we are capturing this input data at the middle. Okay, so we are not capturing it here, but we are capturing it here. So that's a good thing because we are getting this time frame or this time window for stabilizing the input data. Okay, so that's what we wanted from our receiving module. Okay, so that we wanted to capture our input signal at the middle of the baud period. Okay, so that is good. Now we will see that if we are getting the correct output or not. That means we have captured this 10101010 and that should be received at this output port, that is D out. So let's see if we are getting this data at the output D out or not. So this is our output D out. So let's move it down and let's change this radix to hexadecimal so that we can easily visualize. So we are getting 9F, but we are expecting to receive this data, that is AA 10101010, but we are getting something else. So something is not good. So let's figure out why is so. So what I can see that we are expecting 9 pulses at this baud clock because we have generated 8 pulses here. And if we go to the UART receiver and if we see the baud clock generator, so that is data width plus 1 and the data width is 8. Okay, so that's should be 9, but we are receiving 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you see that we are getting double A, so that's what we are expecting after the 9 pulses, but we are getting 3 extra pulses here. So we need to figure out that why we are getting these 3 extra pulses. So if we go to the baud clock generator, and these are the signals that triggers baud clock. So let's see what's wrong with the signal. So let's move start at the last and ready at the last as well. Although this is output, so nothing changes. So main thing is start. Okay, I can see some problem here. So if we notice, then we have one extra start pulse triggered here. So this is good. We are expecting to have this start pulse at the starting when we are about to receive the start bit. But why we are getting this start bit here or this start pulse here? So let's zoom a little. And okay, so we can see some problem here. Okay, so if you see we are at the ideal state, then we are going to this collecting RX state, so that is good, but we are getting this start pulse here once again, so that is wrong. So this is triggered here, and if we go to the code, So this start 1 can only be triggered at this point. So when this falling edge is detected at the ideal state. So at this point, we are at ideal state because the changes will affect after one rising edge. So these changes are here. So at this point, we are at the ideal state, and we are also detecting the falling edge at the data. Okay, so that is also triggered. So that is falling edge is high because that will go low after one rising edge means here. So at this point, this is again high. Okay, let's move to the baud clock generator and let's see quickly what I will do. That I will remove everything here. So delete. And this time I will go to this baud clock generator and I will move all the signals to see what is happening. That is the simplest way of checking that what's the problem, because we knows that there is some problem in the baud clock generator, right? So what I will do that I will restart my simulation. So I will click on this button. So that will restart everything. And now I will run my simulation for again 200 microseconds. Okay, so let's zoom out so that we can see everything. Okay, so what is happening? So we are getting this 9 pulse, so that is good. 8th pulse, 7th pulse, 6th pulse, and then we have triggered this start signal and the counter again reset to 9. So that is why we are getting 3 extra pulses in the output. Okay, so we knows that what is the problem. So we will go to our codes, and then we will open this baud clock generator and let's see if we can do anything to solve this problem. Okay, so pulse control, if start equals to 1, then we are generating pulses. Okay, so it looks like that changing anything here will complicate our transmitter module as well. So instead changing here, what I will do, I will go to the receiver module and I will go to this finite state machines. Sorry, where is UART receiver? So this is our UART receiver. I will go to this finite state machine. Okay, so what I will do that I have to be extra careful while moving from this ideal state to this collecting RX data state. So what I will do that I will trigger the pulse, this start pulse, when this falling edge is detected, else this start will be 0. So all the other conditions, this start will be 0. And when this ready signal is 0, then only we will move to the next state. Okay, if and if, right? So what it will do that it will restrict the current state moving from ideal to collecting RX data when ready is 1, right? Sorry, when ready is 0. Okay, so that was happening that we were at ideal state, right? And then we detected this falling edge, and at the same time we jumped to this collecting RX data, and at this point we still have ready is equals to 1. And because of this condition, it feels like all the data bits has been collected. So this statement gets triggered and we move to this when collected state. And then we jump to again ideal state. So that was the cycle that was happening here. So to fix this, we have added another condition that if ready is equals to 0, then only we will shift to this collecting RX data. Okay, so hopefully this should solve the problem. So what we will do, we will go to this waveform once again, restart everything. Okay, and okay, so I think we need to compile first. So let's right click and then compile all. Hopefully everything is good. Now we will go to this library or simulation and we will select this unit under test and we will select everything. Okay, now let's drag everything into the waveform and run it for 200 microsecond. Okay, so let's see. First we will check the baud pulses because there was some problem. Now we will see if we are generating 9 pulses or not. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so still there is some problem. Okay, so let's see what we are not expecting the problem this time. Okay, I've saved this. Okay, so let's see. I think we have corrected this. So this is baud clock. So we should be able to see 9 clock signals or 9 pulses. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is good. Now I will see this RX underscore sync. So that should be changing at the middle of bit period. So that is changing middle of the bit period because these are 2 successive pulses. And you can see that everything is changing at the middle of the bit period. So this is good. We have already tested the bit period. So this is the half bit period, that is 4.35 microseconds. And this is 8.7 microsecond. So this looks good. And now we will check T out. So this is expected to be double A in hex. So let's change the radix to hexadecimal. So at the last pulse, we are detecting double A. So that is 10101010. So that is good because we are expecting to see this data because we have passed this data at the receiver. So this is good. Next, we will check this IRQ and IRQ signal. So this should be triggered at the last pulse when this data at the output is generated. So we should be able to see double A here, and that should be cleared after giving this IRQ clear pulse. So that is clearing after this IRQ clear pulse, but somehow we are detecting this IRQ once from the starting, although we are expecting to see this after collecting all the data, because if you look at the code of this UART receiver, then the only state that can change this RX IRQ to 1, that is collected state. And once we are here, then after 1 clock cycle, when we are reaching at this rising edge of clock, we should be clearing this because of this input signal or this input port, right? So the question is that why this RX IRQ triggered to 1 before reaching to this collected state. So that is not possible. So let's look when it is changing. Okay, so that's is changing at the starting. Okay, so this IRQ is going to 1 at this point. So till here it is 0 and now it is 1 at this point. And if we look at the current state, because that is the only signal that can change this RX IRQ, and definitely we have some problem here because initially we are at the ideal state, so that is good, but somehow it is able to manage to go to this collecting RX data state, and then after 1 clock cycle, so this is the rising edge, it is moving to the collected state, and then for the next rising edge it's again going to the ideal state, and here we are triggering this RX IRQ. So definitely there is something wrong, so we need to figure out that why this is the problem. Okay, seems like the problem is because of this reset condition, because that is go down at this falling edge of our system clock frequency, and because of this we are triggering to this collecting data state, right? Because at this point our ready, so this ready is high. So till this point this is low, and after this point this is high. So this will be applicable at this rising edge. Okay, so let's move to our UART receiver module and let's see what we can do. And even though this is controlled from the baud clock generator, so even though we can look for the baud clock generator, and I think we can improve this from this module here. So we will look over the when it is here it is functioning. So you can see that this is working here where we are controlling this ready output. So if reset is equals to high, then ready is 0. So we can replace this 0 by 1, and now we should not see the scenario that is looking here. Okay, so let's save this file. So that is baud clock generator. So let's save this. Now go to this project. Now compile all, because everything is dependent on this. So there is no syntax error. That is good. Now go to the simulator and waveform, and I will restart this. So let's restart everything. I will go to this unit under test of UART receiver, and let's delete everything here as well. So let's select all the signals. So baud clock, this, and select everything, or select all the signals. Let's drag them here in the waveform and run our program for 200 microsecond again. And let's see if the problem is solved or not. Okay, so let's go to this point. adjust the zoom area. Okay, so let's calculate the pulses first. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is good. And let's see the sync data. So that is coming, or that is captured at the middle of bit period. So that is good again. Now let's look at the output. So that should be double A at the output when all the pulses has been captured or all the bits has been captured. So that is double A. So that is good. Now look for the RX IRQ and RX IRQ clear. So this looks better now because that is 0 now since starting, and when all the pulses are captured and we can see them at the output doubly, then only this RX IRQ or RX interrupt request is triggered. And when we have given this RX IRQ clear signal or at the input port, then we have cleared this RX IRQ. So that is good. Now let's go to the starting because here we see multiple problems. So let's see if that is fixed or not. So we are at this ideal stage. So that is good. And we have this reset condition for 100 nanosecond. And after 100 nanosecond, we have removed this reset condition. So after this reset condition is removed. Then we have waited for 100 nanosecond once again. So we have this 200 nanosecond point. Okay, so that is good. And till this point, we have at the ideal state. So that is good. Now we are expecting to receive the start bit at this RX underscore sync. So we are getting this start bit here at this point. Okay, so that is good. So for the next rising edge, we have ready signal. So that is good. One again. Now the start signal is triggered here. So that is good now. So when this start pulse is given, we have moved to this collecting RX data after this transaction. So that was causing the problem. So now we are waiting for one more clock cycle to move from ideal to collecting RX data state, right? So this is improved. So that is good. And now this collecting RX data state remains continuously until all the 8 bits is received and captured. So here all the 8 bits has been received and captured. And once we have the output that is double A that we are expecting to receive, then we have moved to this ideal stage and we have also triggered this IRQ request interrupt request signal. And when we have this clear message or clear signal, then we have removed the IRQ request interrupt signal as well. So this is good. And now I am satisfied with the results. So you have seen that we have changed many things in multiple modules. We have adjusted our baud clock generator to work with the transmitter module as well as a receiver module. We have fine-tuned our finite state machine as well to fix the bugs that are unexpected, or even we have not think about those problems. So when we were simulating them in the terms of waveforms, we come to know multiple problems one by one. And then we have digged it down that what signal or what triggers are causing those problems. And then we have fixed them one by one. So this session is a good example that how we can see unexpected things in our results and how we need to think to fix those issues. So that's complete our UART receiver module as well. And now this is the time to compile both UART transmitter and UART receiver in a one single module, so that this module is capable of transmitting the serial data and receiving the serial data over the RS-232 protocol. And we will do this in the next session.